We're going to do more integration by parts today. It's, like I said, this is going to be a long lesson, but I think it's going to be very, very useful for everybody. And here's the reason. Integration by parts can be pretty cool. It's very powerful, but what you guys noticed yesterday is sometimes you have to do integration by parts several times in one problem to make it work out. And today, all we're really doing, the big idea here is we are going to organize integration by parts into a method called tabular integration. We're going to take integration by parts and put it into a table, make it organized to the point that it's much more useful than what we had yesterday. But first, why don't you guys do this opener? It's going to take you a couple minutes. The substitute teacher can feel free to pause the video here, wait till you guys are kind of caught up and ready to go, and then when you're ready, then I'm going to continue on with this problem. So, good luck. Alright, so hopefully that was enough time for the substitute teacher to pause the video. I hope the opener went well for you guys, and let's take a look at what I did. First of all, you've got two choices here for your u, and you've got, or your u and your dv, right? You could say u equals x cubed and your dv equals the natural log of x, or you could have swapped it around and you could have said your u is the natural log of x and your dv is going to be x cubed. Now, I would guess that there's a portion of people in the class that did one of those methods and another portion of the class who did another one. My guess is that more people in the class first tried saying u equals x cubed and dv equals the natural log of x. That actually doesn't work out so well for us, unfortunately. That's the natural choice because making u equal x cubed is kind of nice because it's easy to take the derivative of x cubed, but then we'd have to take the integral of natural log of x, and it's not pretty. So we're going to switch it around from what you might have tried, and we're going to say u equals the natural log of x, and we're also going to say that dv equals x cubed dx. Alright, well at that point what you're going to have to do is you're going to have to say your du is 1 over x dx, and your v is the integral of x cubed dx, which is, of course, 1/4 x to the 4th. Alright, then basically from here on out, all you're doing is you are following a formula. So the formula that we learned in class yesterday was the integral of u dv is uv minus v du. And remember what the whole point of this formula was. The point of the formula was taking a difficult integral, and you're going to split it into two parts. Integration by parts. One part is already integrated, and then the other part is an integral. And hopefully, if everything goes to plan, this integral that you end up with, this new integral that you end up with, is easier to do than the one you started with. And that's exactly the case for this particular problem. I want you guys to, you've probably already did this, substitute in for u. U becomes the natural log of x. dv is x cubed dx. U again is natural log of x. V is 1/4 x to the 4th. And our du is, oh, sorry, my head's in the way here. Let me move out of the way, guys. Sorry. There we go. Our du is 1 over x dx. Alright, then the next step is just kind of cleaning things up a little bit, getting some of that algebra taken care of. So why don't I have it flash on the screen here. And I've got 1/4 x to the 4th natural log of x minus 1/4 integral of x cubed dx. Okay, well, exactly what we wanted to happen occurred here. We wanted this to occur where part of this is already integrated, and then the other part is an easier integral to compute than what we started out with. The integral of x cubed dx, you guys can all do that in your sleep now. And we get, for our final answer, 1/4 x to the 4th natural log of x minus 1/16 x to the 4th plus c. Okay, so I hope that opener went very well for you guys. And what we're going to do is we're going to go on to our new material for the day. If you're not ready for that, you can always ask the substitute teacher to pause the video, rewind the video, whatever you guys see fit. I would make sure to do that at any point during the presentation. Okay. Alright, so we are continuing on with Chapter 6, Section 3, and this is Day 2 of integration by parts, and today is tabular integration. Alright, so let me just remind you guys, we already kind of had this discussion a little bit, but recall what integration by parts really is. Yesterday what we did is we took the product rule, so the product rule for differentiation. We took that formula and we took the integral of it, and that formula that results, that new formula, helps us to do difficult integrals. And so you already used it in the opener, but the integral of u dv is going to equal uv minus the integral of v du. And remember, I'll say it again, the purpose of this is to partially integrate, and then this remaining bit, this integral of v du, hopefully is an integral that's easier for you to compute if things work out how you want them to work out. Okay, and then let me just move my face out of the way here. And like I just said, formula helps us get a handle on integrals that otherwise would have been inaccessible to us. However, here's one thing that was kind of annoying about integration by parts, and you might have found this on your homework. It was kind of annoying when we had to repeat steps, right? It was not too much fun to integrate by parts, and then you get your integral of v du, and then all over again you need to integrate by parts. Not so much fun. And so the whole point of tabular integration, the whole purpose of this lesson, is to give you an organizational model to avoid having to do that. So let me just click to the next slide here. Okay, so remember I had that like really dorky sort of analogy. I said integration by parts has the same instructions as shampoo, and that meant that, so I have, you know, integration by parts shampoo here, and the directions are rinse, lather, and repeat. And this is the instruction we don't really like so much. Why would you want to have to repeat? You know, when I guess when you're washing your hair, why would you want to have to wash your hair over again and over again until it's finally clean? Same thing with integration by parts. Why would you really want to integrate by parts and integrate by parts and integrate by parts over and over again when you could try to get the job done the first time? And so basically what we're doing is we're switching brands of shampoo, and we are moving up the ladder to Pantene Pro V Tabular Integration Shampoo. Basically tabular integration, there's no need to do the repeat step. It's like getting four washes in one or 5 in one. You get 4 or 5, however many you need, integrations by part done in one tabular integration. Alright, I am sorry, this probably is the dorkiest analogy I've ever come up with, but I enjoyed it when I was making it. So now that it's 10:11 at night, it's seeming less like a funny idea, but go with it. And okay. Alright, so guys, what I'd like you to do is for this single slide, none of the other slides, but for this slide, why don't you guys skip taking notes on it and just kind of sit back and enjoy the ride. The reason is we already took notes on this one yesterday, and so there's really no purpose for you to have to go through and write notes on it again, because this was an exact example that you've already seen. So if we're trying to find the integral of x squared e to the x dx, then what we did yesterday is we assigned a u and we assigned a dv. And remember, the strategy was try to pick your u so that you know, a polynomial or a constant is probably a pretty good choice for your u, and then for your dv, typically a good choice would be something like e to the x, sine of x, cosine of x, something that's kind of periodic in nature when you're taking derivatives. And so that's precisely what I did. I said u equals x squared, dv equals e to the x dx. Alright, then what I did is I said du has to equal 2x dx. All I did was take the derivative of x squared to get 2x. And then I took the integral of dv equals e to the x dx. Well, what's the integral of e to the x dx? It's precisely e to the x. Okay, so we did all of that yesterday. And so then it's a straight application of our formula. Okay, where is it? There it is. Okay, so our formula is the integral of u dv equals uv minus the integral of v du. Alright, then it's a straight substitution. U equals x squared, so plug it in. dv equals e to the x dx, so plug it in. U equals x squared, plug it in, etc., etc. And so up on your screen, you should be seeing the step we get after we do all of those substitutions, after we plug into the formula. And then a little bit of simplifying on the right side of the equation is going to give x squared e to the x minus 2 integral of x e to the x dx. Okay, and this worked out exactly how we wanted it to. Integration by parts, part of this is integrated, the x squared e to the x is done, and then we ended up with a new integral that is actually easier to compute. Integral of x e to the x dx. The reason that this is not an ideal situation, and you'll remember this from yesterday, this integral of x e to the x dx, the only way to integrate this one is once again by using integration by parts. So again, you're going to have to assign a u, you're going to have to assign a dv, you're going to have to plug into the formula. That's what's frustrating about a problem like this. Do you really want to keep doing integration by parts over and over again? And in this case, you'd only have to repeat once. You do it the first time, and then you repeat a first time. You do it once, and then you repeat again. So I guess you're doing two integrations by integration by parts. You do two integration by parts, I guess is how you would say it, sorry. But these problems could get a lot worse. You could have to do 4 or 5 or 6 or 7 integration by parts in a single problem, and at that point it would just get overwhelming. And so tabular integration today was going to kind of fix that for us. So I guess the way that we're going to go about it is we're going to take this example that you're already familiar with, this integral of x squared e to the x dx. I'll show you how to do this in tabular integration. You're going to see how quick it is and how convenient, and then we'll try it for 2 harder examples. Okay, so remember from yesterday, just to polish this one off, the integral of x e to the x dx, if you were to use integration by parts again, you'd get x minus 1, that quantity, times e to the x, put it all together, and your final answer is going to be e to the x times the quantity x squared minus 2x plus 2, all plus a constant of integration, a c value. Alright, so if you guys get your pens and paper ready to go again, on this next example, this is going to be new stuff. So let's get ready to go. Okay. And on to the new material. Okay, so example 1, there has to be a better way, right? And there is a better way. And that better way is using a table. So here's what we're going to do. If you take a look at this integral of x squared e to the x dx, what you might notice is really what's going on inside of this integral, this integrand, is made up of 2 functions. The first function, let's say, is f of x, and then we'll say f of x is x squared. And the second function is e to the x. Let's call it g of x. So f of x equals x squared, g of x equals e to the x. And to find this integral, to find the integral of f of x times g of x dx, we're going to use a table. And watch what I'm going to do. I'd like you guys to copy this table into your notes. You should do a very similar thing when you're working through this. So we're going to make a table or a column of derivatives, and we're going to make a column of integrals. So you're going to pick an f of x. I picked f of x to equal x squared, and you're going to pick a g of x. I picked g of x to equal e to the x. And what you're looking for here, this general strategy is similar to what I mentioned yesterday. Your f of x typically is going to be a constant or a polynomial, something that if you keep taking derivatives of it, eventually it's going to kind of go away. Any sort of polynomial, if you keep taking the derivatives of a polynomial over and over and over again, higher and higher derivatives, eventually you're going to get down to a linear term, then a constant term, and then 0. Your g of x doesn't need to have that sort of property. G of x is more, if you have an e to the x, that's a good choice, a cosine, a sine, something that's kind of periodic in nature, something where you're going to see a pattern repeating over and over again as you take more integrals. That's typically what you see. Okay, so I'm going to take my x squared and I'm going to put it into my column. And so that's my f of x, and now I'm going to put it into the derivatives of f of x. So the derivative of x squared, of course, is 2x. The derivative of 2x is 2, and the derivative of 2 is 0. So exactly what I was saying should happen did in this case. we picked an f of x such that if we kept taking more and more derivatives, eventually we got to 0. And now we're going to take a look at g of x. So for g of x, we're picking that to be e to the x, and we're going to keep taking the integral of e to the x. It just happens to be that the integral of e to the x is e to the x, which has an integral of e to the x that keeps repeating. So it just happens to be we picked a g of x that kind of repeats over and over again. Alright, well, let's see how this is useful. Why was it useful making this table? Well, really what you did, you might not have even realized it yet, but making this table of derivatives and this table of integrals, if you put these columns together in a clever manner, you're actually integrating by parts over and over and over again. You're repeating integration by parts so that you don't have to keep doing the formula over and over again. So the integral of x squared e to the x dx, here's what you're going to do. You kind of work down diagonals here, and you can kind of see this color coding I set up. This wasn't by accident. Notice how I went blue, red, and then I went red, blue. That's on purpose. The reason being, this x squared right here is going to be linked to the e to the x that we also have in the table, down a diagonal. So x squared times e to the x, and that's going to go into our answer. And all of the blue ones are going to be positive, all of the red diagonals are going to be negative. You kind of rotate back and forth between positive and negative. So our first term is positive. Then we're going to link together 2x and e to the x, and we're going to use a minus sign there. There's going to be an alternating pattern with your signs from positive to negative. And then our third one, we're alternating back to positive, so plus and then 2 e to the x. Now this general pattern is going to repeat for any tabular integration. Really what we did is we did 2 steps of integration by parts, all in one table. So we worked out the entire integration by parts by filling in this table. And this actually is our final answer. The only thing we need is our constant of integration, and to make the algebra look to make it look a little more algebraically pleasing, I'm going to change this to e to the x times the quantity x squared minus 2x plus 2, which will match up to what you had in your notes yesterday. Alright, well, I'd love to take any questions right now if you guys have any questions. Unfortunately, as you know, this is not a live webcast, so I can't take questions. I'm very sorry about that. So what we'll do is, if you do need this video paused, feel free to have it paused, and if not, then we're going to move on to the next example. Alright, so take a look at this one. Kind of made it a little bit more complicated now. We're going to take the integral of x cubed minus x, that quantity, times e to the negative x dx. And we need to pick our f of x, we need to pick our g of x. Now if I were in the room today, I would ask everybody in the class what's a good choice for f of x, what's a good choice for g of x, and why. But since that's not going to happen, what I'd like you to do is take a couple seconds, take a 30-second break here to think about what you should choose for f of x, think about what you should choose for g of x, and why. By the way, if you guys are wondering, Earl Grey tea that I'm drinking, this is a really good brand of it. And it's not a plug for the company, I don't get paid, but it's the best tea out there. Alright, so hopefully we picked our f of x to be x cubed minus x, and hopefully we picked our g of x to be e to the negative x. And the reason that our f of x should be x cubed minus x is that it's a polynomial, and our f of x choice, we should try for something that as we take higher and higher derivatives of that function, eventually it's going to go down to 0. So a polynomial is a good choice. Alright, so we're going to use a table to find the integral of f of x, g of x dx. Alright, so we've got this table here. It's going to be f of x and its derivatives. It's going to have g of x and its integrals. So I've got x cubed minus x as my first entry. Now you're just going to keep taking derivatives till you get down to 0. So the first derivative of x cubed minus x is going to be 3x squared minus 1. The second derivative now is going to be 6x. The third derivative is going to be 6. And finally, our fourth derivative is 0. So you keep taking subsequent derivatives until you can't go any further. Now we can take a look at g of x. G of x was chosen in a way that you're gonna see a pattern here. There's going to be some repetition. So we chose our g of x to be e to the negative x. Our integral of that is negative e to the negative x. And if you ever doubt that, or if you don't believe me, of course, just take the derivative of negative e to the negative x and make sure it gives you e to the negative x. You can just work backwards and make sure that my answer makes sense. Once you believe that, then keep going up, take the next integral, e to the negative x, take the integral of that, e to the negative e to the negative x, and then take your last integral here, e to the negative x. Okay, so you're going to see kind of a periodic, pattern here. E to the negative x, then negative, then positive, then negative, then positive. That's a good thing. It's going to help us out. And now we have to kind of smash everything together. So what we're going to do is we're going to say that the integral of x cubed minus x, that quantity, times e to the negative x dx, well, we work down diagonals here, remember. And so what we're going to be doing is we're going to be linking together x cubed minus x and negative e to the negative x. And that's going to be a plus in the beginning of the problem. And then the next one, the next term is going to be subtraction. So minus the quantity 3x squared minus 1, and then times e to the negative x. So working down diagonals in our table. Then we're going to switch to positive, so plus 6x times e to the negative x. And then finally, the last one that we can do is 6, so minus 6 times e to the negative x. So notice this pattern, plus, then minus, then plus, then minus. This works for all tabular integration. You're going to have that plus minus pattern every single time. And you work down diagonals from your table until you eventually get to a final entry of 0 in your f of x column. And that 0, you can't go any further. Well, you could, but why go any further? Because adding or subtracting 0 isn't going to change your result. So once you get down to 0, that's your indicator that you're done. And then don't forget your constant of integration, your plus c. And really the only thing left is algebra. You have to take all of this ugliness here, all of this, all of these kind of multiplications and such, and you have to simplify it a little bit. I'm not going to spend a ton of time doing that. I'll just put it up on the screen for you. And what I did is I factored out a negative e to the negative x, and then I was left with a quantity x cubed plus 3x squared plus 5x plus 5, and then all plus your c at the end, and that's all set. Alright, at this point, if you would like the video paused, then please ask your teacher to do so, and your teacher will pause the video for you. And then when you're ready, start it back up when we've got another example. And I'll be right back. Alright, I've got my refill, so time to move on here. Let's go on to our third example. Alright, so our last example, it says example number 2, this is supposed to be example number 3, of course. We're going to find the integral of x squared cosine of 2x dx. And to find this integral, once again, we have to identify an f of x. We have to identify a g of x, which you guys should be thinking about already, is what should I be choosing for f of x? What should I be choosing for g of x? And really you want to be choosing a polynomial for f of x if at all possible. So f of x should equal x squared. G of x should equal the cosine of 2x. and let's work it out. So let me make a table here. And you guys should be drawing a table as well. And we're going to have a table of derivatives for f of x and a column of integrals for g of x. So let's start with f of x. That's the quick one. Let's throw x squared in there. Take the derivative 2x. Take the derivative 2. Take the derivative 0. When you get that 0, that's your indicator that you're done, and you don't have to add anything else to this column. And then you're going to go over to g of x and start doing your integrals, and you're going to work all the way down until you have an adjacent 0. Because remember, you're working down diagonals, so you need to have an entry in this last cell right here, because you need to have it diagonally linked to 2. So we're going to have 1, 2, 3, 4 integrals to put in. I am sorry, I did kind of make an ugly example. I did this because you are going to see stuff like this on your homework. By throwing this 2 into our cosine, it kind of messes around with things, because watch what happens. Cosine of 2x, but then when you take the integral, now you have 1/2 sine of 2x, and then on top of that, when you take the integral again, well, you've got a couple things interacting here. As you're taking successive integrals of sine and cosine, they're kind of swapping back and forth. Cosine to sine, sine to cosine, cosine to sine. But then there's other things happening. This 2 is going to affect the problem more and more as we take more integrals. So for that first integral, we have a 1/2. For this second integral, we have a 1/4, because 1/2 times 1/2 is 1/4. And now, remember, anytime you integrate to go from sine to cosine, you have to take the opposite, so there's going to be a minus in there. And then it compounds even more. You take another integral, and now you've got a 1/8. It's still negative because the integral of cosine is positive sine, so you don't, switching from cosine to sine here doesn't change the sign. Change the sign. S-I-N-E, S-I-G-N-E. That's funny. Okay. Anyway, when you integrate from cosine to sine, it's not going to switch from positive to negative or negative to positive. If you were to do another integral, that's the point where it would be switching sign again. So what you guys should be noticing is there's a lot of little patterns going on in all of these integrals as you take these successive integrals. Cosine to sine, cosine to sine, cosine to sine over and over again. The coefficient is going to start 1, 1/2, 1/4, 1/8, 1/16, 1/32, etc. And then the positive or negative aspect, we're going to go positive, positive, negative, negative. If you made more entries in this column, then it would go positive, positive, negative, negative, positive, positive, negative, negative over and over again. So kind of 3 patterns interacting with each other. Anyway, that's not that crucial. It's nice to notice these patterns because as you're doing more difficult integration by parts or tabular integrations, as you have more and more rows in your table, noticing those patterns is going to make it quicker to fill in the table. But really, you can kind of leapfrog from one to the next. You could just take the integral of cosine of 2x and get to 1/2 sine of 2x, etc. So you don't need the patterns, essentially, is all I'm saying. Okay, I'm going to kind of erase some of this highlighter just because it's in the way. And then what we're going to do is we're going to start working down our diagonals. We're going to start doing our tabular integration, essentially. So let me move my face out of the way. And so to do the integral of x squared cosine of 2x dx, first we're going to start with x squared and 1/2 sine of 2x. Okay, so x squared 1/2 sine of 2x, and then it's going to be minus 2x times the quantity negative 1/4 cosine of 2x, and then plus it's going to be 2 times the quantity negative 1/8 sine of 2x. Okay? Okay. At this point, just add in your constant of integration, and you're all set. If you take a look here, this answer, I mean, it barely even fits on the screen because there's so much going on. I had to work down diagonally. But you could put it together nicely, and it looks pretty good once it's done. It's not that ugly. Let me just... where's my mouse cursor? There it is. Let's move my head out of the way again. Well, it's looking kind of transparent here. Sorry about that. It wasn't supposed to have transparency. But x squared over 2 sine of 2x plus 1/2 cosine of 2x minus 1/4 sine of 2x plus c. Really all I did here... Oh, and I'm noticing a tiny little mistake. I am sorry about this. You might have noticed it too. If you take a look at this red guy right here, negative 2x times the quantity, negative 1/4 cosine of 2x. There's an x there, and it has to be distributed. So there should be a 1x over 2. Let's change that to black so it's a little easier to see. There it is. So it's 1x over 2 cosine of 2x right here. So I do apologize for that. Alright, but the rest of this should be just fine. And let's move on. We can't do any further simplifications really, so we can leave our answer in that form. Oh, there. Now it looks a little bit nicer. I don't know what I did, but the transparency went away. Okay, so x squared over 2 sine of 2x plus x over 2 cosine of 2x minus 1/4 sine of 2x plus c. You know, I said it before, I really wish I could answer questions if you guys did have questions, but it's perfectly acceptable to ask the teacher to rewind this, to watch it over again, or to bring you back to a certain point in the video and pause it, or if you need the video paused so you can catch up and then move on. Guys, your homework for tonight, I'm assigning page 346, 2, 4, 6, 10, and 20 through 28 all. I think you guys are going to be very well equipped to get these done. What I would advise is if you found this material difficult, I would read in the book. The book does a very nice job of presenting this material. So section 6.2, it's laid out very well. If you haven't read the section from the books, the sections from the book yet, I think the authors do a nice job. And so feel free to check that out. The other thing that I would say is if you are stuck on anything, or if there's any sorts of problems that you've been trying that you just can't get a handle on, send me an email, let me know. And there's two things that I can try to do. I can try to post some answers to the web, and I can also possibly take some homework problems, put them in a PowerPoint like this, and record myself working out the problems and explaining them if you guys would find that helpful. You just have to keep me posted about what you need and what will help you kind of get up to speed. In any case, I'll tell you guys all about the AP conference on Tuesday. I hope you have a great weekend, and I look forward to hearing from you guys if you do have questions. On Monday, what you should expect is there's a homework packet and a worksheet. The worksheet's not very long. It's only about 9 questions. The packet is multiple choice questions that are supposed to prepare you for the AP. They're kind of all over the place. There is some Calc A on there. There's a mix of Calc B in with it. And then in class, you're going to be working on some AP problems. All right, then I'm going to end the lesson here. Probably not very gracefully. You're probably going to have to watch me click through and try to turn stuff off. The teacher's welcome to turn this off before I manage to turn it off. All right, end show, discard, and stop. Okay, thank you guys. Have a great weekend.